This is a video about one of the most important, yet least understood, concepts in all of physics. It governs everything from molecular collisions to humongous storms, from the beginning of the universe, through its entire evolution, to its inevitable end. It may in fact determine the direction of time and even be the reason that life exists. To see the confusion around this topic, you need ask only one simple question. What does the Earth get from the sun?
What does the Earth get from sun?
Well, it's light rays.
What do we get from the sun?
Heat. Warmth.
Warmth, light.
Vitamin D. We get vitamin D from
We do get vitamin D from the ultraviolet rays.
Well, a lot of energy.
What does the Earth get from this energy?
Yeah, it's energy.
Energy.
Nailed it. Every day the Earth gets a certain amount of energy from the sun, and then how much energy does the Earth radiate back into space relative to that amount that it gets from the sun?
Probably not as much. I don't believe it. It's just radiating right back.
I'd say less.
Less. I would
Less.
say less.
I'd guess about 70%.
I think it's a fraction. I'd say 20%.
Because we use some of it.
We use some of the energy.
We consume a lot, right?
But the thing about energy is it never really goes away. You can't really use it up.
It would have to break even, wouldn't it? Same amount, yeah.
You know, cause and effect, it'd be equal in some ways, right?
For most of the Earth's history, it should be exactly the same amount of energy in from the sun as Earth radiates into space.
Wow.
Because if we didn't do that, then the Earth would get a lot hotter. That'd be a problem.
That'd be a big problem.
So if that is the case,
Yep.
then what are we really getting from the sun?
That's a good question.
It gives us a nice 10.
It gives us a nice tan. I love it. We're getting something special from the sun.
I don't know. What do we get without the energy?
But nobody talks about it. To answer that, we have to go back to a discovery made 2 centuries ago. In the winter of 1813, France was being invaded by the armies of Austria, Prussia, and Russia. The son of one of Napoleon's generals was Sadi Carnot, a 17-year-old student. On December 29th, he writes a letter to Napoleon to request to join in the fight. Napoleon, preoccupied in battle, never replies. But Carnot gets his wish a few months later when Paris is attacked. The students defend a chateau just east of the city. But they're no match for the advancing armies, and Paris falls after only a day of fighting. Forced to retreat, Carnot is devastated. 7 years later, he goes to visit his father, who's fled to Prussia after Napoleon's downfall. His father was not only a general, but also a physicist. He wrote an essay on how energy is most efficiently transferred in mechanical systems. When his son comes to visit, they talk at length about the big breakthrough of the time, steam engines. Steam engines were already being used to power ships, mine ore, and excavate ports. And it was clear that the future industrial and military might of nations depended on having the best steam engines. But French designs were falling behind those of other countries, like Britain, so Sadi Carnot took it upon himself to figure out why. At the time, even the best steam engines only converted around 3% of thermal energy into useful mechanical work. If he could improve on that, he could give France a huge advantage and restore its place in the world. So he spends the next 3 years studying heat engines. And one of his key insights involves how an ideal heat engine would work, one with no friction and no losses to the environment. It looks something like this. Take 2 really big metal bars, one hot and one cold. The engine consists of a chamber filled with air, where heat can only flow in or out through the bottom. Inside the chamber is a piston, which is connected to a flywheel. The air starts at a temperature just below that of the hot bar. So first, the hot bar is brought into contact with the chamber, the air inside expands with heat flowing into it to maintain its temperature. This pushes the piston up, turning the flywheel. Next, the hot bar is removed, but the air in the chamber continues to expand. Except now, without heat entering, the temperature decreases. In the ideal case, until it is the temperature of the cold bar. The cold bar is brought into contact with the chamber and the flywheel pushes the piston down. And as the air is compressed, heat is transferred into the cold bar. The cold bar is removed, the flywheel compresses the gas further, increasing its temperature until it is just below that of the hot bar. Then the hot bar is connected again, and the cycle repeats. Through this process, heat from the hot bar is converted into the energy of the flywheel. And what's interesting to note about Carnot's ideal engine is that it is completely reversible. If you ran the engine in reverse, first the air expands, lowering the temperature, then the chamber is brought into contact with the cold bar, the air expands more, drawing in heat from the cold bar. Next, the air is compressed, increasing its temperature. The chamber is placed on top of the hot bar, and the energy of the flywheel is used to return the heat back into the hot bar. However many cycles were run in the forward direction, you could run the same number in reverse, and at the end, everything would return to its original state, with no additional input of energy required. So by running an ideal engine, nothing really changes. You can always undo what you did. So what is the efficiency of this engine? Since it's fully reversible, you might expect the efficiency to be 100%. But that is not the case. Each cycle, the energy of the flywheel increases by the amount of heat flowing into the chamber from the hot bar, minus the heat flowing out of the chamber at the cold bar. So to calculate the efficiency, we divide this energy by the heat input from the hot bar. Now the heat in on the hot side is equal to the work done by the gas on the piston, and this will always be greater than the work done by the piston on the gas on the cold side, which equals the heat out. And this is because on the hot side, the hot gas exerts a greater pressure on the piston than that same gas when cold. To increase the efficiency of the engine, you could increase the temperature of the hot side, or decrease the temperature of the cold side, or both. Lord Kelvin learns of Carnot's ideal heat engine and realizes it could form the basis for an absolute temperature scale. Imagine that the gas is allowed to expand an extreme amount, so much that it cools to the point where all the gas particles effectively stop moving. Then they would exert no pressure on the piston, and it would take no work to compress it on the cold side, so no heat would be lost. This is the idea of absolute zero, and it would make for a 100% efficient engine. Using this absolute temperature scale, the Kelvin scale, we can replace the amount of heat in and out with the temperature of the hot and cold side respectively, because they are directly proportional. So we can express efficiency like this, which we can rewrite like this. What we have learned is that the efficiency of an ideal heat engine doesn't depend on the materials or the design of the engine, but fundamentally on the temperatures of the hot and cold sides. To reach 100% efficiency, you'd need infinite temperature on the hot side or absolute zero on the cold side, both of which are impossible in practice. So even with no friction or losses to the environment, it's impossible to make a heat engine 100% efficient. And that's because to return the piston to its original position, you need to dump heat into the cold bar, so not all the energy stays in the flywheel. Now in Carnot's time, high pressure steam engines could only reach temperatures up to 160 degrees Celsius, so their theoretical maximum efficiency was 32%, but their real efficiency was more like 3%. That's because real engines experience friction, dissipate heat to the environment, and they don't transfer heat at constant temperatures. So for just as much heat going in, less energy ends up in the flywheel. The rest is spread out over the walls of the cylinder, the axle of the flywheel, and is radiated out into the environment. When energy spreads out like this, it is impossible to get it back. So this process is irreversible. The total amount of energy didn't change, but it became less usable. Energy is most usable when it is concentrated, and less usable when it's spread out. Decades later, German physicist Rudolf Clausius studies Carnot's engine, and he comes up with a way to measure how spread out the energy is. He calls this quantity entropy. When all the energy is concentrated in the hotbar, that is low entropy. But as the energy spreads to the surroundings, the walls of the chamber and the axle, well, entropy increases. This means the same amount of energy is present, but in this more dispersed form, it is less available to do work. In 1865, Clausius summarizes the first two laws of thermodynamics like this.